Today is the last class of solution chapter. So in this chapter, we will cover the solution chapter for the class 12. So before going to discuss the class, whatever I have taught, just I want to recover that first of all I taught about the solution, what type of the solution could be there, and also the liquid solution and the vapor pressure and Raoult's law, Henry's law, and positive deviation, negative deviation. And also in the last class I taught ideal solution and the non-ideal solution. So today basically we will know about the expression, the concentration of the solution, how we can say a solution is more concentrated and less concentrated, dilute, or how we can um, describe a solution, how we can describe the concentration of a solution. Basically, when we will say, we can actually describe the solution, the concentration of the solution in the two ways. What is the two ways? That is the most important thing. First ways is qualitative analysis. Qualitatively we can say this this solution is more concentrated and is the less concentrated. That means that qualitatively we can say that it is a dilute solution, or we can say it is a concentrated solution. So when we will say it is a dilute solution, when we will say it is a concentrated solution, that means that we know that the solution means there is two component will be there. One is the solid, another is the solvent. When this part will be the less, it is the very less, it will be the very less, then that will be the dilute solution, that will go to the dilute solution. But when the the amount of the solute in the solution will be the high, then is going to the concentrated solution. So basically there are two ways, there are the two comment for the qualitative analysis. What is the two comment for the qualitative analysis? So there is the two comment we can say about the solution in in the qualitatively we can say it is a dilute solution when the amount of the solid is the less in the solution medium, then we can say it is a dilute solution. Or we can say it is a concentrated solution when this amount of the solute will be the higher in the solution medium. So qualitatively we can say it is a dilute solution and it is a concentrated solution. But there is a another thing, it is a quantitatively, that means I have to say how much is there, how much solid is there and how much solvent is there. That means the quantitatively, when we are going to discuss about the quantitatively, that means I have to say how much solid is dissolved in solution. That is the thing. So how much solute will be the dissolved, has been the dissolved in the solution. So quantitatively when we are going to discuss about the solution, so there are the several way. There are the several way. In this way we can say, or we can describe the solution, the amount of the solution, how much solution is there or not. First of all, there is first way is that mass percentage. Mass percentage mean W by W. It is defined in this way: the mass of the component in the solution by mass of the total solution into 100. So percentage, that's why I have multiplied by 100. So what is that? So to discuss the point, the mass percentage, so let us consider there are the two component is there. Okay, suppose the A is a component and B is the another component. Okay, so there is the two component, so A plus B equal to solution. So this solution has been made by the two component, where is the A and the B. Suppose I want to calculate the mass percentage of the A, okay, the mass percentage of the A in the solution. So then what will be the equation? So the mass of the A by mass of A plus mass of B. So that means it is a total mass of solution. Okay, so in this way we can also say the mass percentage of the B in the solution. So let us consider a example. Suppose there is example 10% glucose, 10% 10% glucose in water. What is mean that? What is the mean of the line? 10% glucose of the in water. That means water is a solvent. Here water is a solvent and glucose is solid. Okay, so 10% means, that means that uh, we have 100 gram solution. We have a 100-gram solution. In this 100-gram solution, there is 10 gram of glucose, 10 gram of glucose and 90 gram of water. So in this solution there is the two things, one is the glucose and another is the water. And glucose is 10 gram and 90 gram is water. So total amount is 100 gram. Okay, in this way we have here we have the described the solution in the mass percentage. So another thing is volume percentage. Volume percentage means that V by V. That means whatever we will say in this solution, that will be described in volume. That means it will be the ml. Okay, the unit of the volume is the ml, liter. So here we will describe the volume in ml. Okay, so that will be volume of the component. A specific component is there, volume of the component by total volume of the solution. It is the total volume of the solution into 100. Okay, so we have described the solution in the mass percentage. There was the mass in gram. Okay, here we are describing the solution in the volume percentage. That means we have to describe the volume in ml. So let us consider an example that it is a 10% ethanol in water. What this means? A 10% ethanol in water, 10 percentage ethanol in water. That means the total volume of the solution is 100 ml. Suppose it is in ml. Okay, so the total volume of the solution is 100 ml. So 10% ethanol means there is 10 ml of ethanol is present in this solution and 90 ml of water is present. So here the ethanol is a solute and water is a solvent. So in this way we can describe the solution quantitatively. We can describe the solution in a volume percentage. 10% ethanol in water, that means in this water the 10 ml ethanol is present. So 100 minus 10 equal to 90. So we have the total volume of the solution is the 100 ml. So when the 10 ml ethanol is present, that means 90 ml water is present also is there as a solvent. So in this way we can describe volume percentage. Another thing is that another thing another thing is mass by volume percentage. Mass by volume percentage. So mass by volume percentage means mass equal to W by volume percentage, that means by W. So what is that? It is the mass of the solid dissolves in the 100 ml of the solution. Okay. So when here always we have to say this is a 100 ml of the solution. Okay, 100 ml of the solution. Suppose it is a 15% 15% suppose glucose is there. Okay, glucose 15% glucose. So 15% glucose, that means here if I describe this 15% glucose in water, uh, this solution 15% glucose in water, this solution if I describe by the mass by volume percentage in this way, then we have to say that 15 gram glucose is present, or present is not present, it is a dissolved in 100 ml of solution. Okay, so in this way we have to describe. So another way is that parts per million, that is the important thing, parts per million, that means it is a ppm. What is that? That is a most important thing. That means it is a like that, number of parts of the component is the total number of parts of all component of the solution into 10 to the power 6. So to describe the ppm, to describe the parts of the million, we have to take an example. What is the example? Suppose 1 liter of the sea water contain 6 into 10 to the power minus 3 gram of water. So that means contains about the 6 into 10 to the power minus 3 grams of the dissolved oxygen. That means 5.8 gram per 10 to the power 6 gram of the seawater. So what is mean that? That means that, so it is saying a liter of the seawater contain about 6 into 10 to the power minus 3 gram oxygen. So that means 5.8 gram per 10 to the power 6. That means 5.8 gram per 10 to the power 6. That means that 5.8 ppm. When we are going to describe the parts per million, then we have to multiply by 10 to the power 6 to get the ppm. So when we will use the ppm, that is the thing, when we will use the ppm, when we will getting the some parts, very little amount parts we are getting from a huge amount of solvent molecules, huge amount of the solution. So what it is a saying from the solution is that there is the lots of the seawater is there, but a huge amount of the seawater we are getting the 5.8 ppm oxygen. So when we will try to get, when we will try to describe very small amount of the parts in the huge amount of the solution medium, then we have to use the ppm, that is the parts per million. So this is a one another thing. Uh, so there are also several ways like mole fraction. This is an important thing. Here we will describe we will describe the amount of the solute, the amount of solute in solution in mole. Okay, so the amount of the solute in solution we will describe in mole. Okay, so mole means W by M, that means is gram by molecular weight. Okay, so that is the mole. Mole is W by M, that means the how much amount is there divided by molecular weight. So mole fraction means, so here to describe the mole fraction, let us consider there is the two component A and the B. Okay, so in the solution medium, A has the mole XA and B has the mole XB. So total mole equal to X plus XA plus XB. This is the total mole, total number of mole, total number of mole equal to X plus XA plus XB. So if I want to calculate the mole fraction of A in the present solution, it will be XA by XA plus XB. That means that number of moles of the component by total number of moles, by total number of moles of the all component. So in this example, here we have shown two component A and the B. That's why the mole fraction, suppose the mole fraction f of A equal to XA by XA plus XB. Okay, so in this way we can also say for the B component it will be oh, sorry, XB. So here is the two components. So there is no problem. Suppose there is the lots of component is there. Suppose I am considering that there is I component. So what will be the mole fraction of the I component? So the mole fraction of the I component will be X of I equal to Xi plus X1 plus X2 plus X3 plus dot 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 Xi. So that is the thing. Okay. So and here also another point is that the sum of mole fraction of all component equal to 1. That means suppose the mole fraction f of f1 plus f2 plus f3 plus F4 dot plus of f of I equal to 1. So in this way we can also say the f of I equal to 1, where I equal to 1 to I. Okay. So in this way we can say the mole fraction of the all component will be 1. So mole fraction is a very important thing where we can describe the solution in mole fraction, where whatever component will be there, based on that we have to calculate the mole fraction. Another thing, another point is very important. So this is a molarity. This is a molarity that is described by capital M. Molarity means number of moles of solute, okay, by volume of solution in liter. Okay, so this is the molarity. What it mean that? So molarity M equal to number of moles of the solute by volume of the solution in liter. So if I give an example 2.5 mm, suppose that one, that means that suppose 0.25 m solution of NaOH. What is mean? What is mean of the line? The means of the line is that 0.25 mole of NaOH has been dissolved in 1 liter solvent. Okay, so that means that in 1 liter solvent, 0.25 mole NaOH is present. So so also we can say the unit of the molarity, equal to moles per liter. Okay, so from this unit we can also say the per liter how much mole of the solute is dissolved in the solution. So that is the molarity. Okay, it is described by the capital M. Another thing is molality. This is a molality, and that one is the molarity. Molality is described by small m. Okay, so it is described by the small m. So what is meant by the molality is that number of moles of solute by mass of solvent in kg. So there is some difference in solvent. Here we are describing the molarity as a is a volume of the solution. So that is the thing. Here the volume of the solution in liter. Here we have to notice that mass of the solvent in kg. Here is the solvent and here is the solution. Solution means there is solute also is there, solvent is there. But when we are going to describe the molality, then we have to notice how much mole of solute is present per solvent of in kg, per mass of the solvent in kg. Okay, so when there is saying, suppose 1.00 m of KCl, that means 1 mole of KCl is dissolved in 1 kg solvent. Whatever solvent is there, suppose water is there, so 1 kg water. Okay, so that is the thing. When we are going to describe the molarity, then number of moles of solute by volume of the solution in liter. There is the solution per solution in liter. Okay, this is the moles per liter. But when we are going to describe the molality, that means number of moles of the solute per solvent in kg. So what will be the unit of that? That is the mole per kg. That is the mole per kg. But this kg is according to solvent. But here this liter is according to solution. So this is the different. Okay, so these are the important thing. Where is the mole fraction, where is the molality, this is the small m, and the molarity, it is a capital M. These three description is very important. If what when we are going to describe the solution quantitatively, how much solute, how much solvent is present in solution, then these are the important thing. This is the mole fraction one, another thing is the molarity, another thing is the molality. So next is the important thing. uh, Suppose here I am going to describe normality. Normality is described by capital N. That also the same thing according to the molarity, but there is the different is that when we are going to describe the normality, then this is the number of gram or also mole equivalent. This is the change solid, and this is the volume of the solution in 1 liter. Okay, so normality means how much solute is there, but how much that could be described in gram, that could be described in mole equivalent, that could be described in the mole. When we are going to describe the mole, then we are going to the molarity. But when we are going to the describe how much of the solid in the gram per volume of the solution in liter, then it is a normality. That is the difference between the normality and the molarity. In normality case, the amount of the solute in the solution is described by the gram or the mole equivalent, but in the molarity case, the amount of the solute is described by the mole. Okay, so these are the several process, these are the several quantitative process or quantitative things is there by which we can describe a solution, how much solute is there, how much solvent is there. So after that, here I will stop the class, and also in the previous class I given the some MCQ. So today I will say, or I will solve this MCQ. Okay, the first MCQ is, which of the following statement regarding the ideal solution is false? So this MCQ actually based on the ideal and the non-ideal solution, and also um, there is another properties is there. So basically ideal and the non-ideal solution. So which of the following statement, the first question is that which of the following statement regarding the ideal solution is a false? We are going to the false option. Okay. So ideal solutions obey the Raoult's law under all conditions of temperature and the concentration. We know that this is the correct answer. Okay. So so for the ideal solution, always it's obey the Raoult's law. So there will be the some change in the volume of the mixing is the component equal will be the 0. So the correct answer is the B. Why I am saying that? When we are going to the describe the ideal solution. Okay, when we are going to the ideal solution, that means there is the some criteria. First is that should obey the Raoult's law. Second is that mixing of the volume will be the 0, and then mixing of the enthalpy, that also will be 0, volume will be the 0. So these are the actually obeys the Raoult's law. So these are the, so this is the correct answer, because they are saying the false option. Okay, so for the first MCQ, the answer will be the B. Another MCQ is that, which of the following is not an example of an ideal solution? We know that there is the some example. Okay, so here basically option C is the correct answer. Ethyl alcohol and the water, this is not the ideal solution. Benzene and the toluene is the ideal solution because they are the miscibles, and they also obeys the Raoult's law. When they are going to the miscible, total volume, so delta V mixing will be the 0. So this composition and this composition, they actually obeys the Raoult's law. So that's why these are the ideal solution. But for that ethyl alcohol and this water, they are not the obey the rules. So another MCQ is that a solution which does not the obey Raoult's law is called a non-ideal solution. So this is a correct option, because this is the true. We know that for the non-ideal solution, they does not the obey the Raoult's law. Okay, so this is a true option. Now MCQ 4, which of the following is the false regarding the non-ideal solution? So we know that ideal, for the ideal solution, there is a several there are the several condition. Okay, so the opposite will be the for the non-ideal solution. Okay, so what will be the correct answer? They do not the obey Raoult's law. So this is for the ideal solution is the correct. Delta V mixing will be the 0. That also the for the ideal solution is the correct. But delta H mixing is the 0. Delta H mixing is a 0. So that is option for the ideal solution. That is for the ideal solution. So that will be the correct answer for C. They form the azeotrophs. No, azeotrophs when for the ideal solution, basically the ideal solutions actually forms the azeotroph mixture. What is the azeotroph mixture? I already taught that azeotroph mixture means in the vapor phase and also the in the liquid phase, the compositions will be the same. So this is the ideal solution, and that is the another condition for that ideal solution. So option C is the correct answer. So another MCQ is, which of the following is an example of an non-ideal solution showing the positive deviation? That is the important thing. When there will be show the positive deviation. Okay, suppose there is the two component A and the B. Okay, so when the two component present, so there is A inter attractive force is also is there, BE interactive force also is there, and A and the B, this type of the interactive force is there. When this interactive force is greater, then they will show the positive deviation. But what will be the example. So the correct answer is, this is the acetone. So this is the correct answer, the acetone and the carbon disulfide. So these two components when going to mix to each other and make a liquid solution, then they are acetone acetone. This type of the interactive interaction is greater than acetone carbon disulfide. Okay, so that type of the is going to show the positive deviation. So option 6 is the ideal solution do not form the azeotrophs. So this is the true. Okay, this is the true, but why it is the true? That there is the some condition. Already I already said that ideal solutions forms the azeotrophs. Okay, but ideal solution, but there is a some ideal solution, there is a condition. So this is the exception also is there. So ideal solution do not the forms the azeotrophs. So which of the following is not an example of an non-ideal solution showing the negative deviation? So there is the some example I already here there. So this example is there, but which example is not an example of the non-ideal solution with a negative deviation? That means there is the positive deviation. First we have to understand the question. Not an example of the non-ideal solution showing the negative deviation. That means it will show the positive deviation. So positive deviation will show the carbon tetrachloride and the toluene. Okay. Another thing, the which of the following is true regarding the non-ideal solution with a negative deviation? For the negative deviation, when a non-ideal solution will show the negative deviation, what will be the answer? The interaction between the components is lesser than in the pure component. Delta V mixing will be the positive. Delta H mixing will be the positive. They form the maximum boiling azeotrophs. Okay, so option D will be the correct answer, because when it is a negative deviation, that means the vapor pressures will be the decrease. So when the vapor pressure will be the decrease, then when we are going to boil that type of the liquid solution, then we need the more temperature. Okay, so that's why they form the maximum boiling azeotrophs. Okay, azeotrophs means we have to boil. Azeotroph means the composition of the liquid phase and compositions of the vapor phase will be the same. So vapor phase, that means we have to boil the liquid solution. So negative deviation, that means the vapor pressure is decreased. When the vapor pressure is decreased, then we need to more temperature to the boil. So option D is the correct answer. Now, which of the following cannot form a azeotrophs? So which is the ideal solution? That ideal solution actually cannot form the azeotrophs. So among these four, which is the ideal? That is the answer. The ideal is the benzene and the toluene. This is the ideal because they follows the Raoult's law. HCl and water does not follow. Chloroform and the ethanol is also does not follow. Water and ethanol is also does not follow. That's why option D will be the correct answer. Now, which of the following is the true regarding the azeotrophs? First option is that an azeotroph does not exhibit the same concentration in the vapor phase and the liquid phase. Second option, azeotropic mixture cannot be separated into their constituents by the fractional distillation. Third option, in case of the maximum boiling azeotrophs, the boiling point of the azeotrophs is the higher than the boiling point of the pure, either the pure components. And in case of the maximum boiling azeotrophs, the boiling point of the azeotroph is the lesser than the boiling point of the pure component. So what will be the answer? the azeotrophs mixture cannot be separated into they are the constituents by the fractional distillation. What is means? Azeotrophs means we already said that the compositions of the liquid phase in the vapor phase will be the same. When the composition is same, that means we cannot separate it. Okay, fractional distillations by this process we cannot separate it because the composition is the same. Okay, so this is will be the correct answer for the azeotrophs. So here I will stop the class, and also from the next class I will discuss about I will start the electrochemistry, and whatever problem will be there, if you get you guys can ask me in the next class. And regarding the mole fraction and the molarity normality, uh, I will give the some MCQ. You guys please try. If you have any problem you can ask me. Okay, thank you very much.